Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. So in the last video, we talked about a very important concept, which was linear independence. And basically what this guarantees, or what this says, is that if a set of vectors is linearly independent, then you cannot form one of the vectors in the set through any combination. So you can't form any of the vectors in the set through any combination of all the other vectors in the set. And so that's very important because it begins our whole journey of characterizing vector spaces through representatives. Okay? And so what we're looking for, and so that's going to help us. And so specifically in characterizing our vector spaces in terms of just a few representatives, one property obviously is that, well, somehow we need to get every vector in that vector space from our representatives. So if you recall, this sort of starts to lead us towards the idea of span, which we talked about briefly in one of the previous videos. So basically we need to be able to combine all the representatives in some linear combination to generate all the other vectors in our vector space. And so this means that we need to have a set of vectors which we're going to call S, and S needs to be a spanning set for V. So basically what that's going to mean is that V, that's just going to equal the span of our set S. And we use curly braces here because it is a set. Okay? And so this is what we're going to call a spanning set. So this is a property that we have. And if we have a spanning set, if we have a vector that spans our vector space, then that means that, well, these are representatives. Okay? So we're going to see, for an example, if this set is a spanning set for the set of n tuples, all n tuples. So let's say S equals, we have 1, 0, and then we also will have 0, 1. So these are our two vectors. And we need to check if they span R2. So that's our question here. So, well, you can see that if I take the vector like 5, 4, for example, well, you could take 5 of this first vector and then 4 of the second vector, and you would get 5, 4. And this would hold true for basically any values in our vector. So this would be indeed a spanning set for R2 because with these two vectors, you can create any vector inside R2. Okay? And this is, we say this spans R2, and if we were to constrain them, right? Because right now what we could have is, well, let's say we have 3 vectors now. 1, 0, 0, 1, 1, 1. So we have these vectors, these 3 vectors. And these 3 vectors, well, one of them is unnecessary. This last one here, we don't need it because this can also be, this last vector, we can create it using one of this and one of this. So we don't need this last vector. So this is unnecessary. And in order to efficiently represent our vector space in terms of our representatives, we don't want any unnecessary vectors. So what if we also require that S be a linearly independent set? Well, if we do that, then we don't need this. We get rid of this. And then we just have these 2 vectors. And these 2 vectors, they span R2. They span R2. They span R2, and that means, and since they're linearly independent, that means that we're going to call them a basis. So to formally define a basis, it is a spanning set of vectors. The basis equals spanning set of vectors that are also linearly independent. Okay. So that's basically the main gist of it. Okay. So if we take another example, such as, let's say S, we're gonna say it's 1 1 and 1 minus 1. And so I want you to tell me if these are a basis for R2. Okay, so for R2, are these two vectors a basis? So take a moment to try that out and then come back. Okay, so hopefully you've had a chance to do that, and what you'll notice here is that, well, these two are obviously linearly independent, because remember how we define linear independence for a set of two vectors? They have to be multiples of each other in order for them to be linearly dependent, but they're not multiples of each other, so they are indeed linearly independent. And so we know that they're linearly independent, but do they span R2? Because that's our second condition for it being a basis. They need to span R2. So do they span R2? Well, I mean, you could take you need to try and set some arbitrary values for a vector in R2. So let's say we have a vector u in R2, and it's equal to just arbitrary vectors a and b. Okay, so a and b. Now, somehow we need to get a spanning set. So we need to check if these two can span an arbitrary vector v. So let's say that we have c1, and that's going to be our first vector in our set, plus c2, the second vector in our set, and then somehow some combination needs to equal a and b. So we need to check if that a solution exists for all a and b. So simply this might just turn out to be c1 plus c2 equals a, because you just multiply across, and then c1 minus c2 this time, because it's a minus 1 here, equals b. And so this is our equation, and you can solve this by anything really, Gaussian elimination, or this is pretty simple enough to do it yourself. So if you want to do it yourselves, you can surely go ahead and do it yourself. And so once you do that, if you do it with Gaussian, you should get this, not b, sorry, c1 plus c2 equals a, and then c2 is going to equal 1/2 a minus 1/2 b. And this system, by observation, just purely by observation, you can see that there is a solution for every choice of scalars a and b. So since there is a solution, that means that these two would, there exist scalars that that when used in our system would create a combination for any vector, arbitrary vector or non-arbitrary vector inside R2. So that means that S is indeed a spanning set. Okay, so since we know that S is linearly independent and we know it's a spanning set, then we can say confidently that this is indeed a basis. Okay, and an observation that you should have made by now is to show a set of vectors as a basis for a vector space V, you want to first see the set spans V, and then you can reuse this work because you're always going to get that row reduced form when you're verifying the set spans V. Okay, only in cases like this, I'm going to suggest that you can see by yourself if you have two vectors. But if you were to have 3 or 4 vectors even, then you want to first verify that the set spans V, and then after that you can reuse your row reduced form to check that they are linearly independent or not. Okay? And so now we need to get into dimension, which is just going to be a nice characteristic of vector spaces that'll help us describe a lot of things later on down the line. And so we're going to say that a vector space is finite dimensional if it has a basis containing a finite number of vectors. So in particular, we can say that something like R2, which we've seen, this is finite dimensional because, well, it has a basis with two vectors. So this is a basis, okay? Or even this is also a basis. So since we have a basis with two vectors, right? Well, that means that it's finite dimensional. And it'll logically follow that if it doesn't have finite dimensional, then we're going to call it infinite dimensional, but that is way outside the scope of what we're talking about. So only finite dimensional for what we're at right now. And so that's how we define finite dimensional. Basically, if it has a finite number of vectors in its basis, in its basis. Okay, so let's talk about a theorem here. If you have S, which is a basis for your vector space, and it's a finite set, then any set that contains more than the number of vectors inside S is going to be linearly dependent. And you can kind of just think about this, right? Because, well, S is the most efficient way to represent our vector space. So if you have an extra vector, then that vector has to be able to be created by S. So when you contain that, when you contain that into a set, then it has to be linearly dependent. That kind of just logically follows if you can get that train of thought going. Okay. So an immediate consequence to that theorem is a corollary. So if you have S, and that's a basis for vector space V, and it has n vectors inside of it, then every linearly independent set of vectors in V has to contain n or fewer vectors. Okay? And so this kind of it feels a little bit weird, but it does make sense, I promise. If you have a vector that's a basis, then if you have every linearly independent set of vectors in V have to contain n or fewer vectors. Okay, because, well, if you have more than n vectors, then it's going to be linearly dependent. So I feel like that's a bit worded a bit confusingly, but it makes sense. Okay, then that brings us to another theorem, which is every basis for a finite dimensional vector space has to contain the same number of vectors. Okay, and you kind of have seen this already. This has two vectors, this has two vectors, and any other basis for R2 is going to have two vectors. And why does this make sense? Well, because if this is, they're all the most efficient way. There's you can't have a more efficient way or a less efficient way than that. All the bases have to have the same number of vectors. Okay? And that's gonna tell us that, well, since the number of vectors in a basis for a finite dimensional vector space V is always going to be the same, let's just give that a name, and we're going to call it the dimension of V. And this is going to be denoted as dim V, or dimension of V. Okay? And dimension is going to be a pretty good quantity for understanding vector spaces better. And just to recap the definition of dimension, it's just the number of vectors in a basis for that vector space, because always the number of vectors in all the bases are always the same. Okay, and brings us to another theorem. So if you have an n-dimensional vector space, then n plus 1 vectors equals dependent. So we're going to restate our previous theorem, or our previous theorem in terms of bases. So this is the more formal. In an n-dimensional vector space, every set of n plus 1 or more vectors is linearly dependent. Okay? And so theorem 4, we're going to introduce subspaces into dimension and kind of just confuse it a little bit, but merge stuff into a very useful theorem that we can use later on. So if we say that S is a subspace sub of R3, for example, or R3, well, if our dimension, so if ms equals 0, what does this tell us? Well, then S is just going to contain the origin. So S is just the 0 vector. Okay? So it's just the vector space only has dimension 0 if it's just only the 0 vector. Okay? And then on contrary, if we have a dimension S equals 1, well then in a graphical sense, S will just be a straight line through the origin. Okay, because it's just every vector is a scalar multiple of what we have, so it's just going to be a line. And then if you have the dimension of S as 2, well, in a 3D sense, this is just going to be a whole plane. Okay, so this could be a whole plane, and you're going to have vectors ranging from here to there to there to there to everywhere. And yeah, and in 4D space, 5D space, 6D space, you're going to see the same thing. Continue on and on. And this is just for a 3D space, but the pattern continues, and you'll just get more and more dimensions. Okay? So with that, I want to talk about the standard basis of a vector, which a standard basis of a vector space, which for the case of R2, the standard basis is going to be 1, 0, 0, 1. And so usually you're going to see this just be, well, this is just, it's going to be like the 1, 0, 0, 1, or if it was 3-dimensional, then 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's going to kind of take the form of the identity matrix a bit. So identity matrix kind of, and it's going to kind of look like that in terms of vectors. And so that's going to be your standard basis, which if you've taken physics, then this is kind of just like I and J, the unit vectors. So that's how we're going to define standard basis. And so two more theorems actually. If you have a basis, and if you have a basis for a vector space, and then some vector, then, so I'll write this out. So if you have a basis S, and then you have another vector U which belongs to V, and U can be expressed as some combination of S. So let's just say C1S. No, let's say CS. So C is C is coefficients. It's like a set of coefficients. And then you're also going to have D. So U is also going to equal DS. So a set of coefficients. So this would, what I'm trying to say here is U equals C1 V1 plus C2 V2 all the way to Cn. And then also U equals D1 V1 plus D2 V2. But I'm just kind of trying to write it faster. And so if you have two ways of expressing V as a linear combination of the basis vectors, well, too bad. C1 is going to equal D1 and Cn is going to equal Dn. They are one and the same. Okay? And vectors in a basis, because they're linearly independent, so there's only really one way to represent it, which you can try and prove, but it's just a lot of it is just intuition. Okay, then theorem 6. Let V be an n-dimensional vector space. So let's say we have V and dimension V equals n. Basically, if S, so two parts, if S is a spanning set for V, then some subset of S forms a basis for V. That is, S can be reduced to a basis by deleting from S a suitable number, perhaps zero of vectors. So basically, this is just saying that if you have S which spans V, then there are some vectors that you get rid of to make S a basis. Like we saw with the example of 1, 0, 0, 1, 1, 1, we could get rid of this last vector here to make this a basis while it was still a spanning set. Basically, is the idea it's going for here. And then the second part is that if S is a linearly independent set of vectors in V, then there exists a basis for V that includes in it all of the vectors of S, which means that S can be extended to a basis by augmenting it onto a suitable number of vectors. So this is kind of the inverse of that, the previous part. If you have a linearly independent set of vectors in V, then we can add on some vectors to that, which are going to make it a basis, pretty much, is the idea here. So we add on vectors that help it span the entire space. And that concludes basis and dimension. This video is a bit longer, but there was a lot to cover, so I'll see you in the next.